So far we have done a reaction diffusion framework model to understand tipping points and how early warning signals play out in that system. Okay, so let's now do an alternative framework for studying spatial systems. That's called cellular automata models. So as I mentioned earlier, so reaction diffusion framework is where everything is continuous. The population size is a continuous variable, space is continuous, time is a continuous variable. Now, of course, that requires that you consider all the entities at certain scales for it to make it sensible to use a continuous variable. Okay. Now, in some sense, cellular automata goes to the other extreme and treats everything as discrete. Okay. So the basic idea is as follows. Let's actually look at this in the context of maybe understanding again population growth. So the idea is, and I'm going to introduce a specific model called contact process. So contact process itself is an important class of models from the applied mathematics literature to study population dynamics. I'm going to present one version of it. Okay, I mean, if you read the paper, the original papers in contact process, the presentation could be slightly different. I think it is slightly, in fact, it is different. I'm going to present a slightly different version of compared to what you see there. The basic idea is that we divide the landscape into discrete spatial units. So in the previous case, I was imagining it to be a discrete unit for convenience. Now it's truly discrete. Okay, so we divide the landscape into discrete space. Let's say there are L grids in one direction, L in the other. Sorry, change the notation. You can think of it as L by L landscape. There are L square number of grids, and in each grid you can have only one individual. So we are really looking at very fine scale. If you are in a studying, let us say, population of trees and shrubs, you are really looking at single individual, and the size of this grid should roughly correspond to what a single individual of that species typically resides. Okay, so it's really a fine scale, formulation of the processes, which is in contrast to the previous one where we were looking at certain coarse-grained scales, and we're looking at densities within those. So we assume that each cell can have individuals, and we represent presence of an individual by 1 and absence by 0. So basically each site can have only two possible states, two possible values, 0 and 1. Okay. And so what happens? Let's say there are some ones, 0, 0. They're all, let's say I have assigned some values, and let's say 1 corresponds to presence of an individual and 0 is absence of an individual. Okay, now what? So now based on this, we define in this landscape a birth and death process. The idea is that for birth to happen, sorry, mic got switched off. Oh, it's really okay. White, I'll use the white. So for birth to happen, you need to have an individual present, right? So birth cannot happen spontaneously. That's an important assumption in this model. Of course, makes perfect sense. So the idea is that we randomly choose a site in this landscape, and if the randomly chosen site is occupied, if it has a value 1, 1 can give rise to 1, 1. It can give rise to a birth in one of the neighboring cells. Okay. For example, in this case, if the randomly chosen neighbor was this, randomly chosen site was this, it could give birth in one of the 4 neighboring sites. Of course, it cannot give birth to a site where it's already present. Okay, it can actually give birth in one of these 3. Okay, so the way the rules of this model is defined is that I pick a random site, and if the random site is occupied, then you look for one of the random neighbors, and if that random neighbor is unoccupied, okay, then you reproduce in that empty cell. Okay, this is the simple birth process, and that also happens with a probability p. Is this rule clear? 2 important points to note in this are that the birth is happening locally. So these 2 1 0 are not chosen randomly in anywhere in space, but they're actually chosen and in a local neighborhood. If you generalize it to saying, oh, it could be anywhere in the space, you sort of go back to one of the previous models we have studied. Okay? I mean, the space becomes irrelevant now. But because we want the space to be relevant, we look for the neighbor only in the neighborhood. Yeah. So I choose any of the neighbor, and if that neighbor is unoccupied, that's when the birth happens. All the 4 neighbors are chosen with equal probability. So, I mean, I think I want to clarify that I'm not choosing the 3 with equal probability. I'm choosing all the 4 with equal probability. And if the chosen one is empty, then only with probability p reproduce. Okay. Okay. This is the birth. And of course, if only birth is present, things will just keep on growing. There has to be death. So with some probability, the same guy you had chosen would also have died. Okay. So there are now 2 ways people formulate this. In fact, the most standard way is that you assume that the birth in the empty neighborhood happens at probability p. Alternatively, you just die with the probability 1 minus p. Okay. And when the death happens, it is irrelevant whether somebody in the neighborhood was occupied or not. Therefore, I'm not even referring to any neighbor here. Okay. And you can sort of generalize this model to sort of replace this with an independent parameter d. So you can then have 2 parameters p, a birth probability p and a death probability d. So that's one way you can sort of make it slightly more general. But as you can imagine, physicists and mathematicians want to reduce the number of parameters in any model they build. So 1 minus p is what you would often encounter in the literature. So do we need anything else? There is some birth happening, local birth, and there is some death happening. Do we need anything else? What do you think if I keep on doing this? What happens? It's on P, okay. So let's see what happens. That's what we would like to understand. So of course, what you can do is you can go to a computer, you can tell the computer, hey, look, I have all these grids and I have all these very simple rules. Please tell me what happens after very long enough. Ask the computer, but maybe before even ask the computer, we can try to make some calculations on our own to have some expectations. Is that reasonable? So remember that these 2 are stochastic birth and death processes. So until now we were looking at deterministic processes, but here both the processes are stochastic. Okay, but to make some reasonable, to make some sort of predictions for the of what the model will do, we can resort to something called an approach called mean field approximation, which is actually what Sudipta covered yesterday in some using the examples of chemical reactions. So this is also some kind of chemical reactions, but they are written in the space. So we'll do something called a mean field approximation. So it's really bizarre in some sense. The whole point of what we want to do is to have explicitly space. Okay, but we will write down a mean field approximation nevertheless of this spatial stochastic process to have some sense of what do we expect as we change P. That's the basic idea. Okay, so what is the idea of mean field approximation? Does anyone who knows tell me what's the idea of a mean field approximation? So the mean field has a hint. It is that, hey, look, if you look at local scales, there are these very discrete entities. Mean field, mean as is basically average. Field, the word field usually comes from the physics literature, where people study particles and fields. Okay, so we want to understand the mean values of all these variables. That's the mean field variable, and how that changes over time. Okay, that's where the name comes from. And when we study mean field, we are ignoring the variation. We ignore the variance, fluctuations. We only focus on the mean. So how do we go about this mean field approximation? Okay, there are, I can write this down directly the way physicists try to do, but I thought maybe it will be useful if I make connection to what Sudipta did yesterday, which is master equation. Do you all remember master equation? What does master equation tell us? It basically tells how stochastic variables change over time. Okay, so let us define. So what are the stochastic variables here? It's ones and zeros. The values are ones and zeros. We can define, we can ask this probability of a site being occupied by 1. So P of 1 can be defined as probability of a site being occupied by 1. Likewise, we can define P of 0 as probability of a site being occupied by 0. Okay. Can we write an equation for how this probability changes with time? This need not be same, but imagine I have started off with very few ones. But if the P is very, very large, I would imagine that it will increase. Initially, the probability of finding 1 was very low because I have initially input very small number of ones. But because of the birth process being highly probable, the ones will now spread over, and I can ask, how will this now change over time? So basically, this is a function of time. So therefore, I can ask, how does this change? Okay. Now, to understand this, the idea of master equation is really helpful. So just to recollect, the idea of master equation is that if you are interested in some variable, you want to calculate the rate of change of that stochastic variable. Now, what you do is you will write down all the inflow rates to the state of interest. Okay, and then you subtract it by outflow. Okay. Okay. So can we now enumerate these two? What is the inflow and what is the outflow? So now inflow is basically whenever 0 becomes 1, right? Okay. So basically we need to calculate this in terms of the inflow rate. What's the, this is the inflow, this is the outflow. Actually, basically, it's very two simple processes here. So we can try to write that down. So what is this? Can somebody try this out? It's an exercise of, how comfortable you are with the techniques you're learning in the course of the school. Okay, that's a very good point. So the site has to be empty for it, and then there is a probability P, right? What else? Are these the only two things? What else do you need? Huh? What about this? So you need to have somebody to germinate or somebody to sort of, give birth to, right? Basically, so the randomly chosen individual in your update scheme must be occupied, and then there must be a transition from a neighbor must then transition from 0 to 1. Okay, so omega is a transition rate in my terminology. So the randomly chosen individual must be occupied, and the neighbor should transition from 0 to 1. Okay, and then what's the outflow? Or the death, basically death terms. Basically, that is, what is that? It must be occupied and it must die. And that is basically D times P1. Right? So probability of death is D or 1 minus P, depending on how we write. Now, what is this omega? So for the empty site to turn 1, of course, the neighbor must be empty. That means it is P of 0. And then that must in turn get a birth on that site. Okay. So basically, dp1 of dt is equal to p of 1, p of 0 times p minus d times p of 1. Does everyone agree with this? Okay, so what is this now? Okay, now here is, let's simplify the notation a bit. Let's call p of 1 is equal to rho. So density, basically what is 1? 1 is probability of being, 1 is an occupied site. P of 1 means probability of being occupied. If I assume that the entire landscape has a density rho, P of 1 has to be rho. Okay. And what is P of 0? People are very tired, or you think it's so easy, I don't want to tell you what it is. So a site is either in one of these two states, right? So it is 1 minus. Okay. So now let's substitute these in the equation above. And depending on whether it is DRP, you have a slightly different equation. Okay. So this is the mean field approximation for the model we just described, the stochastic birth and death process we have just described. Okay. Now we know what to do with this. We're now an expert in dynamical systems, right? What will you do with it now? Find the fixed points and then find the stability. Can you do this? Yeah. And if you combine the term, it's basically. Is that what you found? Yeah, you're right. But I would like others to solve. Yeah, right. Yeah, we'll also find a transcritical bifurcation. But please solve it and let me know. So please try to plot the following. What do you think is a bifurcation diagram to plot here? What should be on the x-axis? What's the P, birth rate? Okay, and x-axis could be rho star. I would like to see how this looks like. problem solved. Are you able to solve it? I hope most of you are able to solve it. I'll just do it now. So you can simplify this equation, take the linear terms together, have rho times p minus d times p rho square, and you can make it look like a logistic equation. Okay. And if you do that, you will find that R, what we call R in logistic model becomes P minus D. What we call K in logistic model becomes P minus D by P. Okay. And first thing you note, before we go further, what's important to note here is the following. In a logistic model, we wrote R, the intrinsic growth rate, and K as two independent parameters. What does this tell us? This shows that they're not independent parameters. So if you start with the birth-death model, the intrinsic growth rate and the carrying capacity, they are not independent parameters. They actually they basically have the same features. They come from the same parameter values. Okay, and it also connects those birth and death process rates to the population level parameters. Okay. And you also see that for the intrinsic growth rate to be positive, P has to be greater than D, right? Otherwise, so basically if you have done it correctly, you will find that 0 will be you can see it from the equation here, right? If the R is negative, 0 will be the stable equilibrium. And if P is greater than D, up to 1, 0 becomes unstable. And then for P greater than D, this becomes positive. It reaches some maximum value, which is 1 minus D by P, 1 minus D. That's the maximum value it can reach. It reaches sort of in this fashion. Is that right? If I have made any algebraic calculation. So this is basically a transcritical bifurcation. Okay. So as you change the birth rate, the population size changes continuously. Any questions on this? So now, if P is some measure of environmental driver, like rainfall or some other drivers, and reducing that will lead to a population extinction, but in a gradual or a continuous way. So this model cannot capture the tipping points, right? It can only capture a gradual, continuous transition. Okay. That's what the mean field approximation says. Remember this, the actual model is this, the stochastic birth-death process. I have ignored everything about stochasticity when I have sort of, averaged the stochastic part here. Okay, that's really important. And there is another crucial approximation we make when we write down mean field approximation. That's not very evident in the way I have described so far. So basically, look at the following: this birth term in particular. So how does the birth term happen? You need to find a random site, see if it is occupied. That's what this term was representing. And then we check then our random neighbor. If it is empty, we will make it occupied, right? And we wrote that as P0 times P. Is this correct, by the way? Is this probability calculation correct? This is correct. But is this correct? Or did I make some assumptions in doing so? Because I've been saying it's an approximation. What is approximate about it? So remember that P1, okay, so P0 is conditional on a neighbor being 1. So that is really what I am looking at. But what I have done in the subsequent calculation is that I have assumed that P of 1 is rho and P of 0 in the neighborhood is 1 minus rho. So I have assumed that whatever is applicable for the entire landscape is applicable to two neighbors, which means I have ignored the spatial correlations. Okay. So when I'm doing this calculation here, I'm going to assume that P of 1 is rho, which is fine. But P of 0 in the neighborhood of 1 is 1 minus rho. When I wrote this, I made an approximation that I can calculate these two probabilities independently, ignoring the fact that they are actually very, very close to each other. So I ignored spatial correlations. And that is why it's called a mean field approximation. Okay. And which means that anything this tells, I have to take it with a pinch of salt. It's not guaranteed to be true, but it's a good starting point. And if we actually go and do simulations, okay, and check, and people, as I said, people typically do it for d is equal to 1 minus p. If d is equal to 1 minus p, you should redo the calculations. You will find the following. You will find that this changes in the following way. In a very simple way, nothing really fundamental way. It changes, it predicts that p must be equal to half. Until then only you will have 0 population size. For p greater than half, you will have a finite population. And of course, it it's just rescaling. It's really nothing fundamental, right? So it just shows a value of half because d is equal to 1 minus p. And then if you now do actual simulations and check the value at which up to which this is present, you will find a slightly different value. What you will find is that up to 0.6, you don't find, you will always go to extinction. You will not find any, any sites with living organisms. But after that, you will find a very similar pattern. So you will find that the transition is continuous, except that the critical point of the transition is not 0.5, it's around 0.62. Okay. And for, I think for some, if I'm right, for 1D or 2, I forgot which dimension, there's actually analytically exact result. Is that right? I think I forgot the exact, it's possible to prove the exact value of this for some dimension. I don't remember which dimension, 1 or 2D. Oh, exactly, is it? Oh, for 2D also? Oh, okay, okay. So it's not analytically. So I think this is for 2D in simulations. 0.62 is in 2D. So I think it must be possible to analytically. Okay. So this is what you find. But all of this, how unfortunately doesn't capture tipping points. Now the question is, how do you change this model? What do you think is missing in this model? Because if you want to understand how spatial organization happens in systems with tipping points, you need to have a good model, right? This model doesn't even produce tipping points. It only has a gradual transition, continuous transition. So how do you think we will change this model? Any suggestions? Which is not linear? What should it be then? Huh? Oh, that's very complex. Sigmoidal form. Okay. Which one? Sorry. Oh, here. But I want to change. I don't want to change the equations directly. I want to change these two, and then I want to derive the equations. Okay. Okay. So basically, he's saying that this is fine, this death is fine, but I'm more likely to die if I have some neighbors around me. Do you think that will, you should try it for sure? So you're basically saying, 1, 0 becoming 0, 0 is fine, like this. But 1, 1 becomes zeros or whatever, 0, 1 at a probability higher than, if this was D, this is some D prime which is greater than D. Is that what you're saying? That means, there is more crowding, no, for there's more competition, therefore you're more likely to die. That's one modification you can do. You should try this out. And once you do this, you should be able to write down another master equation and then make some predictions. Okay, that's a reasonable start. Any other suggestions? Okay, so it turns out that what he's saying will not work, but you should try it out on your own. It will just exaggerate, it will increase the depth, it will basically move this to further right. Okay, but what you want is something different. No, you want to make this more nonlinear. Right? You want this to survive. You want this branch to survive and become more nonlinear. Right? How could you achieve that? So the trick to achieve that is the idea of positive feedback. So what do you understand by positive feedback? Just immigration is positive feedback? Is mere immigration positive feedback? So if there is one, then there's another one. Okay, fine. Okay, but let's avoid immigration in this model. Let's think of birth and death. How do we do this now? How will it? Say that again. One. Okay. Getting close. Okay. I think it's a positive feedback, but in temporal positive feedback. What about spatial positive feedback? Okay. What about you? Okay. Okay. I think all of you are getting at the same point that, but it's slightly different words. But I think what you guys are saying is fine. So basically, we are assuming that if an individual will reproduce in an empty site nearby, but what we will now say is that in addition, if there are two neighbors, a neighboring empty cell has an even higher chance of an additional chance of having it occupied. So this is a Q is a new parameter I am introducing now. So 1, 1, 0, because now this 0 is surrounded by two ones, we will convert it to a 1. So by increased birth rate when there are, so this is in addition to what we already have. By the way, so it's a new rule. We are adding new birth rule on top of what we have. It's not the only one, by the way. Okay. And what else can we do? That mimics this for the depth. A pair will make the nearby empty site a higher probability. What else? And this could, for example, in the context of plants, for example, would mean that a cluster of vegetation holds water better. Therefore, there's a higher germination rate in the neighborhood of a cluster of plants. Okay. That's one way to interpret a phenomena like this. Instead of just one individual being able to reproduce, it has a higher probability. What else? For the death. They have loneliness. So you can say there is reduced, whatever, so basically the idea is that there's a reduced death rate. So, you remember we had a death rate of D, when there was an individual, a solitary individual had some D probability of death. But what we will say is that, what did we say there? 1 goes to 0 at a D rate, but 1 has a lower chance of going. It's not D, it's D into 1 minus Q. Okay. Of course, I could have added one more parameter here, but to reduce the number of new parameters, I'm using the Q again. So this reduces the birth. Basically there is an enhanced birth rate because of neighbors. There is a reduced death rate. Okay. Now, for this model, I will not do the entire calculation. I will just write the final form of the equation. Because it will now have many more terms. Not many more terms. Just one more term. Can you guess what's the new term we will have? Can somebody guess? So we had a linear term and a quadratic term, right? What do you think we will have now? I've given a hint already. Make D debate. Okay, I'll just tell you what you will find. Okay. After some algebraic simplification, we will, if you know to the mean field approximation, again P minus D times rho. I'll just bring this here. Minus P minus Q minus QD times rho square minus Q rho cube. Okay. Okay, so this will be your this is the new equation, and as you can see, it has a cubic term now. And the moment you have cubic term, so linear and quadratic is like logistic model, right? Linear, quadratic, cubic will be like the alley effect model. Okay. Q is a measure of positive feedback. So basically now the right hand side will have this form under some conditions. It depends on the coefficients. It can now reach this form, the entire right hand side here. F of rho, the function of rho can have this form when some conditions are met, meaning basically the Q has to be greater than some threshold value and P has to be greater than D, obviously, and Q has to be greater than some threshold value. And if that happens, then you can have three equilibrium points, three fixed points, of which 0 and this will be stable. So now if you now try to do a similar diagram like this, what happens is that you will find, so 0 will be one stable equilibrium. You have an unstable branch and you have a upper branch. So this Q has to be greater than some Q threshold, and Qt depends on the P and D. Okay. So basically what this simple model shows is that to achieve bistability, you need to have strong positive feedback in the system. And in fact, nothing new about this. People have long argued, how do multiple stable states coexist under the exact same condition? It was also a question I asked on Monday, right? For example, if you find that under the same environmental condition, if two very contrasting states can arise entirely based on initial conditions, we must be able to argue what are the processes that drive it. Okay. So in the context of, for example, a population like this, what this means is that when the population size is low, it's unable to compensate for the deaths. But whereas if the population size is If the Q is large, meaning the positive feedback is large, what can happen is that that you can form a cluster of ones which will maintain themselves because of positive feedback. And that's the reason why you have this branch, but that cluster had no use in the original model without Q. So the clustering effect is now the positive feedback effect of cluster of ones is what actually maintains bistability in this model. Now, if you think of models like lake models, people argue that there are processes about nutrient cycling that maintains between very contrasting states like clear water lake and a very turbid lake. And that often has to do with some nonlinear responses and positive feedbacks between sedimentation and the what is called, I forgot the term, what is it, recycling of the sediments. Okay, so under exactly same conditions, that recycling phenomena can be either very weak or very large. So you can have very different types of phenomena that in turn affects the entire system state. And something same with the climatic systems. Once you are in a hot climatic regime, that becomes self-stabilizing, and it becomes hard to go back to the low temperature regimes. Even if you sort of reduce, let's say, carbon concentration, for example. For example, this entire, I don't know how many of us, and I think next week Tim Lenton probably will talk about this, right? What's called thermohaline circulation. It's a huge circulation system in the oceans, and that is maintained by a set of positive feedback processes. If that positive feedback processes are broken below a threshold value, it now goes to a different state. Now, to set up the entire positive feedback again is incredibly hard. So this is an important link between positive feedbacks and tipping point in terms of the processes. So anytime you hear, oh, a system shows tipping points, always ask yourself, oh, what is the underlying positive feedback process that is maintaining these alternative multiple stable states, and what are the and then how can we explain the transitions and the stable states based on those? Okay, so that's one part of it. Now, of course, once you have the equations, for the mean field limit, all the ideas of critical slowing down will continue to hold because they're the same equations. They have similar bifurcations. But here is something interesting. I will now want to show. I think is the zoom on. Yes, it is on. I will share my screen. I will show. We can ask a following question. Forget about all these analytical approximations. If I just simulate this, how will this look like? That's what I will now try to show. Okay. Can you see there? Oh, excellent. Okay, cool. So let's focus on only one of them. The left-hand side is a simulation of this model where the Q is either 0 or very small, okay, with some value of P. So you can see that there are, first and foremost to see that, there is no homogeneous, as not every cell is occupied. Roughly things are spread without any directionality, but there is some amount of clustering that you are seeing, right? Some places have more individuals, there are lots of empty gaps. And that is a consequence of that local birth process. In the middle of that bare patch here, in the middle here, of course, nothing can spontaneously come out. So that will remain empty unless one of these clusters moves there, or and it grows. So this is how. Let me just play the animation again. So we started. This is some value of P. I think not very large value of P. Once we started off with very large number of occupied cells, but because the initial values were very high, the depth was dominating. but eventually they reach a steady state. So even what is important here is that the steady state is also stochastic. It is continuously evolving. It is not that there is one fixed configuration in space where they settle to. They are continuously small. These clusters are growing and dying and so on. Now, on the right hand side is where the positive strength of positive feedback Q is quite large. You can see that, I think between the two, the value of P was same. The baseline birth rate was same, but here you have a larger Q value. So what you see is that there is a lot more clustering now compared to this. Okay, and we haven't shown the values here, but what you will also see is that for the same value of phi, it can now maintain much higher population densities. Okay, so this is the effect of positive feedback. It leads to clustering. It also leads to existence of bistability and more generally multiple stable states, where you would otherwise expect only one stable state. Okay. Now, what you can see here is that you can already, so it already has various visual features that the mean field model cannot even sort of get there, right? For example, can you tell me what are the features here you are seeing that of course makes no sense at all in the mean field model context, like the ODE model context? What if I had given you this, what can you measure from this? Something you can measure here that you can't measure from a time series data. Yeah, and spatial distribution. Can you think of more specific metrics? One is heterogeneity, you're right. Correlations, exactly. Spatial correlations, not just temporal, spatial correlations. Very good. What else? Huh? Yeah, variance. Yes, a lot of variability in space. Correlations, variance. Let's say that this is a connected set of individuals, and then let's say I count the number of individuals in this cluster. Is that same here and here and here? So one can look at the size distribution of these clusters as well, right? You can look at the average value of the sizes. You can look at the entire distribution also. Okay. Okay, and then in fact, in one paper in 2007, which became very popular, they argued, they did not use mathematical arguments, entirely based on simulations. They sort of argued the following. Okay, let's say if this is some driver, like that P we have, let's say we have this kind of a bifurcation diagram. If you only plot the mean value, if you plot the average occupancy in the entire landscape, this is how it looks like. So this paper argued that if I look at the patch sizes, these cluster sizes, it actually shows a power law when you are far from the bifurcation point. But however, as you get closer, they argued that it becomes more of an exponential distribution. Okay. And the fact that you find a power law, in some other papers, people argued that it relates to the phenomenon called percolation in physics literature. Okay. But all of this was done entirely using numerical simulations. But there was no underlying mathematical theory. Okay, and it's always really important to understand the limitations, power as well as limitations of numerical simulations. So analytical calculations we have done cannot say anything about these clusters and stuff, but the numerical simulations can. But numerical simulations can, because they are specific to parameters you choose, specific to models you choose, also can sometimes give you bizarre results. And this was one of those, I think. For example, in one of the later work, in fact, done by my student, we found that this relationship between distance to the bifurcation point and the cluster size distribution is really not robust at all. In fact, you can actually have power law even right here. In fact, for systems with stronger positive feedbacks, which are more prone to abrupt transitions and critical transitions, in fact, you often find power law or cluster size distribution at the critical point, at the bifurcation point, not really away from it. So basically, so it's important that when we are studying these systems using numerical simulations alone, it's entirely possible that we arrive at a very system specific solution, but not a very general solution. Okay. But I think the take home message is that the moment you have spatial data, you can begin to measure things that are just impossible in a temporal, if we had only temporal context. So therefore, in systems where spatial data makes sense, it's important to sort of, I think, also study spatial patterns and how they behave, and how can we make sense out of those. Okay, I think we have reached the time, so I will stop here. In the afternoon, in the tutorials, two of my students will show a package where one can measure many of these quantities. They will also show maybe, I think, simulations and also how to apply this to a real data set, right? So I will stop here. Thanks, everyone.
So if we zoom in or zoom out from that spatial figure, and means some kind of scale invariance relevance, so is it possible to get from that spatial?
Yeah, you see, you're actually absolutely right. So the images you saw, they have some fractal dimensions.
Yes, yes.
They have some fractal, the clusters you saw, they are not necessarily of dimension 2. So they actually have fractal dimensions. You're absolutely right. So in fact, just an unpublished work of one of my students, what she showed was that if you increase the positive feedback, the fractal dimension gets closer to 2, meaning they're more round shaped. Whereas if its positive feedback is less, it's closer to 1. So in the contact process, the fractal dimension is closer. I don't know the exact number, but closer to 1. But the positive feedback, when the strength of Q increases, you get a value of fractal dimension closer to 2.
So is it become more relevance when a system close to the critical point?
Does it have relevance?
Yes,
is that your question?
Yes, yes. Means,
I think in an indirect way, right? Because we know that systems with high positive feedback are also more likely to exhibit multi-stability and therefore transitions. So therefore, I think the fractal dimension does have implications for tipping points. Thanks. Any other questions? Yeah.
That was forming cluster. Is it a cell?
Say that again.
I'm saying, sir, was that a cell which was forming clusters?
Was there a cell forming?
You have shown us, sir, that a clustering was happening. So I'm saying, is it a cell or some other inside cell, some biomolecules have formed cluster?
No, this is that model I described, ones and zeros. That's all.
So means we are not really talking about any biological model here.
It is a biological model, but there are
cells
no
were forming clusters.
Chemical. When I say cell, I don't know whether just to be very, I don't mean the biological cell. So the grid is also called a cell.
So
the grid space where I have written 1 and 0 is also called
that
a
box
cell.
you're calling a cell.
Yes, yes, yeah. Sorry for the confusion. Yeah.
So yeah, so you said that
the mathematical modeling, just analytically, you can't capture this sort of clustering. But this is true of the mean field models. But in principle, you can do analytics, right? Or are there fundamental limitations on?
I don't know how you would start with the birth-death process and then construct an equation for the cluster dynamics. You can do an ad hoc model of cluster dynamics, but the connection between the parameters and the process at the local scale to cluster size, I do not know. But maybe it exists. I don't know.
So maybe you can conduct a birth-death process where the state of the system is the matrix, the entire matrix, instead of, and that will capture the
L
cluster.
square values,
Yeah, I mean, on paper you can do it for any n, no?
but you should also be able to write on a paper. Okay. Yes. It'd be great to know how to do it. Yes. Huh.
So how does this get extended to multiple species?
Yeah, you can extend. Absolutely, yes. Like the phage bacteria model of Sandeep is one such. You can do predator-prey models. You can, yeah, there are models, predator-prey models as well. Yeah, and depends on, what you want to capture. For example, can two species occupy the same site or not? Depends on your assumptions. If it's a predator-prey, that means the predator is probably eating the prey, right? So you have to make some specific assumptions to the system you are considering. You could also say, yeah, so it's entirely possible and there are such models.
I guess I've only seen it in context of predator prey, but
Yes.
one of the questions which mechanistically doesn't really make sense is sort of evolution of cooperation, particularly in microbial populations. And the major problem with that explaining mechanistically is you're susceptible to cheating if you're cooperating.
Yeah.
But this clustering sort of
Yes.
you think of a way where you can get
Yes. People have used these kind of models for that, for explaining cooperation. And clustering does, absolutely right. Yes, helps. Yeah. And I have done only one work on that. One of my previous students worked on a model where, so here the individuals are stuck on a lattice or a cell, right? They can't really move. They can only reproduce. And that's the only way of movement here. But you can also have an active movement of agents. And there also clustering helps in the cooperative process. Even though they're moving and mixing a lot, but when they're moving, they move as a cluster. Therefore, they can survive as cooperators. But I think Martin Novak's group has done quite a bit of work with this type of models with cooperators, cheaters. Yeah. Mm-hmm.
Species that is row.
Huh.
So if I consider, let's say, two species, row 1 and row 2, and then obviously the concept of competition and mutation will come.
Yes.
Then,
we'll actually get Lotka-Volterra equations.
It's just simple Lotka-Volterra in
Mean
one and
field
N2.
will have Milk-Volterra.
In one and N2. But I think that will make the problem much more complex. Can we still keep ourselves in the XY plane, or a concept of volume will come? I don't know.
Well, if the animals live in 2D plane, we should model in 2D plane only. But you're right, that as a third dimension makes sense in some cases, yes. And it also makes, because they now have a shared space, the coexistence becomes really hard between two competing species. We'll actually find coexistence in an extremely narrow range of parameter values. There are two species competing on the space. Yeah.
Some death or birth. So this is kind of oscillation.
Oscillation means, I would use the word oscillation when there is periodicity.
Periodicity, obviously.
It's stochastic. I wouldn't say it's oscillation.
Okay. So can we model these with some stochastic oscillators and couple them and make a network and find the same type of result?
It's worth investigating because what you need to remember, I think, here is that the then the connectedness depends on the distance here, right? It's all, not any two clusters are connected at the same strength, and the strength reduces with the distance. And in fact, it's very local. So, two clusters can merge and they can also split, but that's only local, right? It's not like a network model where any two can be connected.
No, actually, we can
Yeah.
do local coupling also.
Space constraints a network of connections, but it is, I think, interesting approach to try. And there are models of cluster dynamics where they ignore space, and that also yields some useful insights.
Sir, here we have added a say positive feedback, and we
Mhm.
could see such a transition. Just changing the, because in the death rate we are saying it's a linear term. If we change it to a non-linear term, would it have a similar impact as the updation rules have?
So are you saying let us change the individual rules or the equation?
Because no, just the equation. We are keeping the updation rules same, and we are adding non-linearity in the equation.
See, but they must correspond, right? No, I
Yeah,
mean,
they must correspond. It will just change the probability, probably. I think
Mhm.
the probability, the amount of the death probability and the reproduction probability would be changed, but the
Uh-huh.
updation rules are kept same.
But if the update rules are same, I can't change the equations. I mean, the equations follow from the update rules, right? There is a very clear correspondence from the update rules to equations. Like if I'm changing equations, I must also change the update.
Then it will not be like if I'm saying just one is going to 0 with the probability d,
Mhm.
then how come it can differ?
I don't think I understood the question.
I'm saying that here we are considering that after death, one goes to 0 with the probability d.
Yeah.
If I want to change the dynamics, I want to change the updation rule here.
Uh-huh.
Can it go to like 0 going to 2 or 1 going to 2?
What is
Is
2?
that
I have
possible?
defined what is
1
2.
plus 1, say I have two
Okay.
species on a site.
That's not part of, so you have, so one can change the model rules and incorporate more complex interactions like this, but this model doesn't have, but it's possible to incorporate what you're saying, and then one should carefully derive the equations. I think it may have interesting features. I don't know, I haven't studied it. So we'll take a break now.